So in this video, you're finally going to get some answers. If there's a question in your lab packet, this is where I am going to answer it and also go over the data from the lab activity that I did with my brothers. So the first question is to come up with a prediction or hypothesis. For this one, I came up with kind of two hypotheses. Remember, I always say the easiest way to come up with these is to make it an if-then statement. So if X happens, then Y will happen. The ones that I came up with were if the bear is in water, then it will get bigger. And the second one I came up with was if the bear is in salt solution, then it will get smaller. Next, let's go over the data and calculations for this part. So my sheet got a little wet with all the gummy bear water around, but this is what my data table looks like. I went over it in the last video, but you can see I have a section for the water bears, the salty bears, and then I did this with my brothers. So each of us has a section, and I just used our initials. We also did mass because we had a scale with us. So I have the original mass, day 2 mass, original height, day 2 height, original width, and day 2 width. I done goofed up in the beginning and put my data in the wrong box, so that's why it's a little messy up there. If you want to pause and you can kind of look at the data, that you can go ahead and do that now. And then I am going to go on and go over how you do the math for the calculations. So you have your calculation hint box on the page that follows the procedure and the introduction in your work packet. And on a separate page, I went through and did that work. So I also went through and I kind of did my own little hint box that might help you guys. So in general, what you have is your end measurement. So the measurement that you took on day 2, and you're going to subtract the start measurement. So this is my day 2 measurement. So let's say day 2 height. So I start with day 2 height minus my start height, and then I divide that answer by my start height. I do all of that, and then I will multiply by 100 to get the percent that it changed. So again, I'm going to walk through a few examples of this. You subtract your start measurement from your end measurement. Divide by your start measurement, and then multiply by 100 to make it a percent. And then what will that number even mean? So if the end measurement is greater than your start measurement, then your percent change will be positive. And that means that your gummy bear got bigger, that measurement increased. But if the end measurement is less than the start measurement, then your percent change will be negative. And that means that measurement actually got smaller. Again, this is the general formula we're going to use. They have the same thing, just written in a different way in your packet that I sent home. But if you want to pause and use this one, if this one just looks simpler to you or something, you can go ahead and pause and write that down now. This is the general formula for percent change. Okay, so now we're going to go over how to do these calculations. Remember, it's the same, so I wrote out the same thing that I did on the back of the page, but instead of measurement, I wrote in what exactly it was. So here we're doing end mass minus the start mass divided by the start mass times 100. I am going to write in the actual numbers just above where I wrote the words in different colored markers or pens, for each type of measurement. And I am just going to do the measurements that I took for mine, and and then I'll just show you the others at the end. So for my end mass, I had 9 grams. I put 9G because it's always important to use your units. And then for my start mass, I had 3 grams. And then, so I have 9 grams for the end and 3 grams for the start. And then I'm dividing that by 3 grams as well and multiplying it by 100. Feel free to use a calculator. I don't know where I put mine. Here we go. So if you want to use your calculator, all you would do is hit your 9 minus 3 equals, and then divided by your 3 grams again, equals, and then times 100. So this is equal to 200%. Remember, if it's a positive number, that means that our gummy bears, that measurement got bigger. So our gummy bear's mass increased by 200% for the water bear. Next, we're going to do height. So the end height was 3.7 centimeters. So I just wrote that right above. End height, 3.7 centimeters. Our start height was 2.3 centimeters. And then we also divide by that same start height. And then we're just going to multiply by 100. So we take 3.7 minus 2.3, and then we divide that by 2.3, and then we multiply by 100. I'm just going to round to the nearest whole number, so 60.8 becomes 61%. So my water gummy bear's height increased by 61%. Finally, we're going to do the water bear's width. So we take our end width, which was 1.8, and then we subtract our start width, which was 1.1, making sure I'm putting my centimeters in there. And then we are going to divide by that start width, 1.1 centimeters. So again, taking my calculator, 1.8 minus 1.1 equals, and then we're going to divide that number by our start, which was width, which was 1.1. And then we're going to multiply by 100 and round to the nearest ones place. So 63.6 becomes 64%. So my gummy bear that I put in tap water, its mass increased by 200%, its height increased by 61%, and its width increased by 64%. Now, I'm going to use these exact same formulas. So the end mass minus start mass divided by start mass times 100. I'm going to use that same formula for mass for my salty bear. The only difference is going to be the numbers. So instead of rewriting out the whole word, all the words this time, I'm just going to write the numbers. So looking at my data table, my end mass was 3 grams for my salty bear, and so was my start mass. So 3 grams minus 3 grams divided by our start mass, divided by this start mass, so 3 grams, and I want to keep my parentheses, and then I'm going to multiply it by 100 to make it a percent. Now, if you really think that you need to type this into the calculator, I'm not there to stop you, but let's think about it. 3 minus 3 is 0. 0 divided by any number is always 0. So you're going to have 0 divided by 3 is 0. And then 0 multiplied by any number is also 0. So what you have here is 0 times 100 is still 0. Which makes sense because a percent change of 0 means it didn't change at all. And we went from 3 grams to 3 grams. So there was no change. Next, let's look at the height. So for height, we had 2.4 centimeters for our end height. And we also had 2.4 centimeters for our start height. So we have basically the same kind of scenario as we just did for our mass. There was no change, but I'm still writing out the math of our end minus our start divided by our start multiplied by 100. But again, it's the same kind of scenario as with the mass. So we have a percent change of 0% for the height. Finally, looking at the width, we have our end was 1.2 centimeters and our start was 1.1 centimeter. We are going to divide by that start of 1.1 centimeter. I'm pretty sure my marker is dying right in the middle of this. And then multiplying by 100. All right, I'm grabbing another marker because that one, of course, chose right now to die. So times 100. And then, so that ends up being, I can't do that math in my head. So that is 1.2 minus 1.1 divided by 1.1 times 100. So that ends up being a change of 9% if we're rounding to the nearest whole number. So our for the salty bear, our mass didn't change, the height didn't change, and the width actually increased by 9%. I am going to show you the calculations I did for the other part, or for my brother's data, just so you can see what it all looks like. And that way, if you want a little bit more practice with this, you can do that. I will circle the answers in the corresponding color. And note this one in particular, it has a negative sign, so that means that this mass actually decreased after sitting in the salt solution. And I will discuss the results in the next little section of this video. Okay, so we have come up with our prediction, or predictions, and we have looked at our data and done some math to see what that data tells us. Now let's discuss what that means. Specifically for my data that I got with my brothers, out of all of our data, just looking at it, all of our bears that soaked in water got bigger. So they all increased their mass, they all increased their height, and they all increased their width. So what we know from osmosis is that that means that more water had to move into the gummy bear. Water moved into the gummy bear because there was a lower concentration of water in the gummy bear to start. So we had a lot of water outside of our gummy bear in the beginning and not as much inside. To fix that, to get it back to equilibrium or to balance it out, a lot of water had to move into that gummy bear. So that is why we see such a big change, why we see those gummy bears get so much bigger, because it's like that water balloon. We took a whole lot of water and we had to fit it into the same container. So our gummy bear, or just like a water balloon, stretched to fit the rest of that water. On the other side, our salty bear. So most of them either stayed the same or they didn't change at all. What that means is that they were pretty balanced already. So the salt solution that we made had a very similar water concentration as the gummy bear. So bringing it back to the two hypotheses that I made, remember, that was if the bear soaked in a water cup, it would increase in size. So my data supports that hypothesis. But I also said that if the bear soaked in a salt solution, it would get smaller. But for the most part, that didn't happen. What it actually happened was that it stayed the same. So an idea to do another experiment with this would be to see how much salt I would have to put into a solution, or how much more salt I would have to put in the solution to get the gummy bear to actually shrink. So I would be trying to find what the salt solution or salt concentration is in the gummy bear and making the water around it saltier so that there's more water in the gummy bear than outside. And then, because osmosis is water moving from high concentration to low concentration, when the water moves out, the gummy bear would actually shrink. First question, on the bottom of your calculation and data table page, it says, based on your data or class data, where is the concentration of water molecules highest? In tap water, salt water, or the gummy bears? So this was our research question. And the answer is that it's the tap water. And that's because the bear that soaked in water was the one that changed the most, because there was the biggest difference between the water concentrations inside the gummy bear and outside the gummy bear with the cup that just had tap water in it. And then the question on the next page asks you to draw a diagram or a set of diagrams that support your answer from question 1. So I just drew this little picture of, don't mind my bad drawing of my little gummy bear, but I have a key. So my little circles represent water molecules and my little X's represent other molecules. So here I have it labeled that this is the tap water, and there are a lot of circles in the tap water, and there aren't as many circles inside the gummy bear, but there are a lot of X's in the gummy bears. So osmosis happens and water moves into the gummy bear because there's less water here to start. And because the different molecules in the gummy bear cannot leave the gummy bear, they stay there, and there ends up being less water molecules on the outside than there was to start, and more on the inside than there was to start. And this helps balance the gummy bear or get it to equilibrium. And then our final question, number 3, in this lab and in the diffusion across a membrane lab that you did with Mr. Tackentine, You explored how substances move across a simulated cell membrane. Compare and contrast how these two models, gummy bears and that dialysis tubing, represent a selectively permeable membrane. And the answer to that is that both let water pass through their membrane easily, but other larger molecules cannot pass through. And that's it for that. I hope you guys had fun doing the lab, or at least watching my brothers and I try to do the lab. I hope that we can get back to school and do actual labs in class, but if not, let me know if you guys enjoyed this, and I'll maybe send you more labs like this to do at home if, unfortunately, we have to continue these school closures. Have a nice day, guys!